Okay, so new topic for today. Recall last time we were talking about inner products, and just a quick reminder of what inner products are. Inner products are another abstraction. Inner product spaces are another a related abstraction that we create, and it's another way to acknowledge that patterns that we notice that happen in Rn, similar patterns happen in other contexts, and the similarity of those patterns in other contexts is are very valuable. Being able to do these kinds of algebraic calculations that start off being exclusive to Rn, being able to do the same kinds of calculations in other contexts is super powerful. So here's the next related idea. Let's talk about the idea of orthogonality. So recall from Rn, two vectors are orthogonal if their dot product is 0. Well, in an inner product space, totally analogous definition. In an inner product space with inner products playing the role previously played by dot products, two vectors are orthogonal if their inner product is equal to 0. Now, very importantly, what inner product? Well, the inner product associated with that inner product space, right? So it's going to be different in every inner product space. Okay. All right. So I think, like I say, pretty plausible definition. So along those same lines, what do you suspect an orthogonal basis would be? Well, it's exactly what it sounds like. It's a basis in which the vectors are all orthogonal. Exactly what it sounds like. So pairwise orthogonal. Take any two vectors from this list. They're orthogonal to each other. Okay. Now, here's one that is a little bit different. Let's talk about an orthonormal basis. It's got to be a basis. The ortho suggests it's got to be orthogonal, but there's an additional requirement, what we call the normality requirement. Normal, by the way, is an odd word. This word gets used in a lot of different contexts to mean different things. In this case, despite the fact that in Math 212, normal vectors are considered perpendicular, right? In this case, normality refers to the magnitudes being 1. This is consistent with some of you have had a stat class, and you might have heard the term being used, a normalized distribution. So it's kind of along those same lines. So this is an additional requirement, and it turns out that this stronger requirement gives a concept that has some really powerful applications. So we're going to spend some time today talking about orthonormal bases and what you can do with orthonormal bases. Okay. All right. So first, a picture. That's a picture of what an orthonormal basis looks like. Again, the orthogonality refers to the fact that pairwise these are all orthogonal. And the normality refers to the fact that these magnitudes are all 1. Okay, couple of examples. The standard basis, easily checked, is an orthonormal basis for Rn. Easy exercise, not at all hard to persuade yourself. Pick any two of those vectors, they're clearly orthogonal. Pick any one of those vectors, the magnitude is clearly 1. Super easy example. Here's a less obvious example. This little trio right here, that is an orthonormal basis for R3. Pairwise, there's 3 different calculations you have to do to check the orthogonality. These are orthogonal. These are orthogonal. Easy dot products. And then also these are orthogonal. Easy dot products. You can do those on your own. Next requirement, though, the normality. This one has magnitude 1. This one has magnitude 1. And this one has magnitude 1. And sure enough, details all check out. This is an orthonormal basis for R3. Okay. How are we doing? Is everybody on board? Any questions? Okay. All righty. Okay. Moving along. Okay. There are two really big properties that we're going to talk about for orthonormal bases. Here's the first one. This is a huge theorem. I'll talk about why after we get through doing it. So suppose you have an orthonormal basis for your vector space. Oh, excuse me. What did I just say? What a silly statement. You can't have an orthonormal basis for a vector space if something is merely a vector space. Orthonormality refers to the inner product. This V must be an inner product space in order to even talk about orthonormality. Right? So anyway, something to keep in mind. So given an inner product space, V, which asterisk, of course, is also a vector space, but we need that inner product structure. Then for any vector in that vector space, there are a couple of calculations that will always line up, shockingly. One is if you compute the coordinates of that vector. And keep in mind, coordinates always means with respect to a basis. We're talking about this basis here. So, coordinates are a calculation that y'all recall, right? The idea of coordinates is we ask, how can I write this vector as a linear combination of those given basis vectors? We have a notation for it. Here it is, right? Those are what we call the coordinates of that vector. It's a calculation that's based on linear combinations. Okay. On the other hand, here's a different calculation. Projections. Now, I refer you back to one of the first things that y'all talked about in Math 212. Think back to early Math 212 and how you compute the projection. Sometimes they call it the component of one vector and the direction of another vector. And it's done with, in Math 212, dot products. In this context, inner products. Right, same thing. So in the same way that when you have unit vectors in Math 212s, projections are computed with dot products. Likewise here, with these unit vectors, don't forget we have an orthonormal basis, therefore normal, therefore all unit vectors, projections are computed by the inner products. Okay, so what this theorem says is that these two things will always be the same, right? Because of the basis being orthonormal, these two completely different calculations will give you the same values. And it's really a pretty surprising result if you think about it. Again, now let's just remind ourselves what is the sort of the point of view on each of these pictures. On the left side, what I have in blue here, this is about linear combinations of vectors. This over here is about dropping perpendiculars. Completely different seeming calculation. Okay. Let me draw a picture of that for you. So given a vector, here's a vector that we were considering. For example, we have the basis given here. V1 and V2 is our basis. If I want to view V as coordinates, I want to view it as a linear combination of these vectors V1 and V2. I'm asking about, roughly speaking, and let's not worry about the details, roughly speaking, a calculation that takes place on a parallelogram. Right? If V is a linear combination of V1 and V2, then we're talking about some multiple of V1 plus some multiple of V2. That makes a parallelogram. So that's where the coordinate calculation here comes from. Come from looking at that parallelogram. Whereas, on the other hand, how do we compute projections? Projections are about dropping perpendiculars. Right? Roughly speaking, that's the picture that computes projections. There's the V1 projection, and then, analogously, you might say, here's a picture that you would draw to compute the V2 projection. So, again, completely different pictures. You wouldn't think that these things should be the same. They're just completely different calculations. Shockingly, when you have an orthonormal basis, everything lines up. And it's not the biggest surprise in the world. Again, you look at this picture and you think about, well, I'm dropping perpendiculars versus I'm drawing parallelograms. But you can see how if this were a right angle, right, if this were a right angle here, then the parallelogram would be a rectangle, and then drop in the perpendiculars. You see how these calculations are starting to look like they're on kind of the same picture instead of on two different pictures. So geometrically, I think there's plausibility in that point of view. Plausibility is not a proof, of course. Let's prove this theorem. It's not a hard proof. It's actually a pretty straightforward proof. A couple little details we have to worry about. I'm going to start off by, again, we have this vector v. And let's suppose I know its coordinates. Let's suppose I know how to write it as a linear combination then of the basis vectors. That's what it means to have the coordinates. Keep in mind the coordinates then are these numbers, C1 through Cn. Okay. Okie dokie. Well, that's what this vector v is. So I can write that vector v right there. And now let's look at the projections. How would I go about finding these projections? Well, projections are computed with inner products. That's how I compute the projections. And so it's just a matter of computing here. And nice things happen. Don't forget that we know that we have an inner product, and inner products have the feature of being linear in each entry. So this is a linear transformation, and therefore linear combination on the inside, linear combination on the outside in the usual way. There's just linearity. Secondly, now recall that we have an orthonormal basis. We'll use blue. An orthonormal basis, specifically then an orthogonal basis, and because it's an orthogonal basis, I know that all of these inner products here are 0. The inner product of any basis vector with any other basis vector, all 0. Directly as a consequence of the orthogonality. Lastly, don't forget this is not just an orthogonal basis, it is an orthonormal basis. Each one of these vectors has magnitude equal to 1. Therefore, each one of these vectors itself inner product with itself. 1, right? That's the normality. So this great big expression that we have here, this expanded inner product in computing a projection, massive simplification. Most of the terms cancel because of the zeros. This factor of the self-inner product disappears because it's a factor of 1. And all we're left with is that coordinate, very conveniently. So this projection then is the corresponding coordinate as required. So that's how the argument goes. Really nice result. Okay, so let me give you a couple of reasons why you should care about this. First, a quickie. Let's look at this example here. And, given a vector v, how would I find its coordinates? With respect to the basis on the previous page, that basis on the previous page, recall, was these vectors. Kind of a weird basis, but okay, let's suppose we're doing business with this basis. How would I find the coordinates? How can I write 1, 2, 3 as a linear combination of these vectors? Now, you can view this as a chapter 1 problem. How do I write that as a linear combination of these? Write down a vector equation, rewrite it as a matrix equation, you row reduce. There you go. Look at those numbers. Those numbers are kind of inconvenient. There's square roots and fractions. Right? So, you could do that, but it would be a little bit inconvenient. The theorem above is what saves us that trouble. This theorem above says if you're interested in coordinates, don't worry about it. Just compute projections. They're the same thing anyway. And so rather than computing the coordinates, I compute here the projections. That's just dot products. Super easy calculations. And therefore it's easy to find the coordinates. They are the same thing. Everybody on board? gives you a computational alternative. Like I say, sometimes finding coordinates is hard. In this case, what makes the finding of coordinates hard is the arithmetic's a little bit inconvenient. And fine, so be it. Now you might be thinking, yeah, I'm going to have a computer doing these kinds of things for me, right? The moment I get out of Math 216, the computer does all such calculations for me in the future, and that's true. There are sometimes, however, structural reasons why finding coordinates is hard, right? Think back to when we were talking about, independence arguments. And it's one thing to make an independence argument if you're talking about Euclidean vectors, because with Euclidean vectors, you just write down the coordinates, and the question pretty much instantly resolves to a matrix problem. But remember how much harder things got when we were talking about a list of functions. If it's a list of functions where, it's not like something convenient like polynomials where effectively you have coordinates, a list of functions, how do you turn it into a matrix equation? There is no matrix equation to write down particularly quickly. And we found ourselves in quite a bind. They got resolved by this argument called the Gram-Schmidt. Well, so the point is, things that are trivial in Rn, row reduction, become kind of intractable in other vector spaces, such as vector spaces of functions. So adding in different techniques, the Gram-Schmidt and all. So that's kind of what happens if, imagine that instead of trying to write a Euclidean vector as a combination of Euclidean vectors, what if you wanted to write some wacky function as a linear combination of other functions? It's a hard problem, right? So that's what this is good for in those cases. In those cases, the coordinates might be an intractable question. The projections are not that bad. Okay. So now let me say one other thing about why this theorem is great. You may recall that I made the observation that inner products are important because of powerful applications, and I listed two of them. Fourier series, from a certain point of view. Fourier series comes from inner products. Image compression, certain kinds of image compression. Big deal, right? Come from inner products. And in both of those cases, this is the next step in that direction. Again, there's a lot of details. We don't have time to go through all those details. But this is one of the big ideas. This is the next step toward how to use inner products as a big idea in, for example, let's say image compression. You view images as vectors in an inner product space. You try to write those images in coordinates as linear combinations of a nice set of other images, as a basis set of images, and you compute how to write those coordinates, how to figure out how to write that image as a combination of simpler images by computing inner products. But that's an essential tool then in doing those constructions. Okay. All right. Questions? Okay. All righty. By the way, along those lines, so as this applies to Fourier series, I actually wrote some exam questions here or there. And I have to admit, I don't remember which one it was or how long ago. But there's at least one old midterm exam question that, roughly speaking, outlines a framework for how to use this to compute Fourier coefficients, and then students have to kind of fill in the blanks to complete that process. So if you want to see how this is used to find Fourier coefficients, you can just go find the old exam question that I described. Okay, moving along. So here's the next big thing that we can do with orthonormal bases. I'm going to make a definition, something called an orthogonal matrix. This is an orthogonal matrix. If a certain condition holds, the condition is that the column vectors make an orthonormal basis. That's something you could entertain. By the way, of course, this is in Rn. Just talking about Rn here. If the columns of a matrix form an orthonormal basis for Rn, the resulting matrix is called an orthogonal matrix. Now, first a terminological discussion, complaint, confession. Doesn't it feel like this should be called an orthonormal matrix? I feel like this should be called an orthonormal matrix. And I've brought this up with colleagues on a couple of occasions. The complaint being that, hey, what if someday we actually need to talk about a matrix whose columns are not necessarily orthonormal, but are merely orthogonal? What we call such a matrix whose columns are merely orthogonal. And roughly speaking, the reaction I got was, yeah, but that's not, that's not a thing. That's not interesting. Why would we ever be interested in that? Who cares? It's got nothing to do with anything that ever comes up. Right? Well, my complaint still stands. If nothing else, the word orthonormal here would at least kind of be a more motivatable term, right, than orthogonal. But historically, this is what it's called. It's anyway, a little bit unfortunate. So heads up, you have to remember henceforth that when you hear about an orthogonal matrix, right, you should not assume from the lingo that means that the columns are merely orthogonal. That's not what it means. An orthogonal matrix, I know it's weird, is a matrix whose columns are orthonormal, which is a stronger condition. All right. Weird. Okay. Neat fact about orthonormal matrices. Oh, gosh. See, I've got it in my head. That's how I think about them. Okay, orthogonal matrices. If a matrix is orthogonal, that matrix has the feature that its transpose is its inverse. That is a really surprising fact. Really surprising fact. First of all, super convenient. Let's take a moment to recognize how nice that is. You remember how hard it was back in Chapter 1 to compute inverse matrices? You write your matrix here, you put the identity matrix next to it, and you go through a row reduction process, and once you get down to the identity as a reducer echelon form, then whatever ends up here, that, because of fancy arguments with elementary matrices, that has to be your inverse matrix. Here it's much simpler, just transpose matrix. It is super convenient. Inverting an orthogonal matrix is just transposing. Okay, so really, really surprising. Let me show you how to prove this. It almost seems too good to be true. How could this possibly be true? But it's really no big deal. I mean, let's look at the definition. Orthogonal means that the columns form an orthonormal basis. Right? So this thing here, the columns are an orthonormal basis. A transpose is it's the same thing kind of turned sideways. If A has columns that are an orthonormal basis, then A transpose, those rows are the exact same orthonormal basis. So this is what that calculation looks like. If you want to multiply A transpose times A, keep in mind if these are inverses of each other, we can confirm that one way or the other by computing this product and confirming it's the identity. So really all you got to do is multiply this out and confirm that you get the identity matrix. And there's only two possibilities. One possibility is that you are looking at a diagonal entry. Let's look at this product here. If you are looking at a diagonal entry, then you're going to be dotting a row with a column, corresponding row with corresponding column is this dot product. But wait a minute. The rows here are basis vectors. The columns here are basis vectors. If it's a diagonal entry, we're looking at the same row, the same column. We're dotting the same basis vector with itself, in which case you get 1. So this matrix product on the diagonal just has to be 1. So a bunch of 1s there. On the other hand, if you are off of the diagonal, you're over there, or over here, anywhere off of the diagonal, you're going to be dotting one of these basis vectors with, well, a different basis vector. The row number is not equal to the column number because you're off the diagonal. That means that the left basis vector and the right basis vector are different basis vectors, and different basis vectors are orthogonal, and therefore their dot product is 0. So, as required, you get 0 off the diagonals, 1 on the diagonals. Direct calculation, this product is the identity matrix, and therefore these matrices are inverses of each other. It's just brute force. How are we doing? Is everybody on board? Neat fact. Okay, one little detail I do want to discuss. Let's go back up here to the definition. Here's the definition that I made of an orthogonal matrix. Here's what I've stated as my first theorem about orthogonal matrices. Note how different these statements are. The definition is a statement about what are the column vectors, and the theorem is a statement about how do inverses work. Very different statement. Which one should be made the definition, and which one should be the theorem? It's kind of subjective. I chose to make this the definition because despite the terminological awkwardness, at least the orthogonality tells part of what you know is the motivation for what we're calling this. The word orthogonal, that kind of connects, however imperfectly, to what we're defining this thing to be. Right? So I think this is at least a somewhat motivatable terminology. The book reverses these. It doesn't really matter. It's an equivalent definition. Remember, I talked about equivalent definitions on the first day of class in one of the first pre-lectures. The book makes this the definition of what it means for a matrix to be orthogonal. And my only gripe with this is, if you look for the connection here, why would we take a matrix that has this property? Why would we choose the word orthogonal? It doesn't really leap off the page at you, right? If you just look at this concept, the idea that a matrix might have an inverse that is a transpose of itself, you could think of a long list of other terms or words that would seem naturally to connect to the idea of the transpose being the inverse. Right? Long before you came up with the word orthogonal. So I just feel like this is it's hard to motivate the term if you make this the definition. Okay. Anyway, it's a personal complaint. Do be aware though that the book makes this switch for the purposes of midterm exams and final exam. This is the definition that we'll use for Math 216. Okay. And they, of course, are equivalent. Okay. So what can you do with this? The big conclusion that we're going to use here is the following theorem. If a matrix is orthogonal, then it preserves dot products. Before I prove this result, let me talk about what I mean by preserving dot products. It's right here in how this algebra works out. This matrix A preserves dot products in the sense that if you take a couple of vectors v and w, if you look at their dot product, and then if you subsequently say, okay, yeah, but let me multiply both v and w by a first, and then compute the dot product, you get the same value. Right? So the action of multiplication by a does not affect the dot product. The dot product before, the dot product after, same thing. So that's what we mean by preserving dot products. Kind of a odd result. We'll talk about why we care about that in just a moment. First, let me prove the result. The first line of this proof, I'm in the wrong color. First line of this proof uses a formula that we have not written down before. We haven't had any need for it before now. It's not a big deal. Let me just write it down for you here. In general, A dot B is equal to what you might reasonably call A transpose B. And just to be clear, what I mean by A transpose is, of course, we view A as a vector. We tend to write vectors vertically. And by A transpose, what I mean is take this vector that we are writing vertically, interpret that as a matrix that consists of a single column, and transpose that to make it a matrix that has a single row. So I mean literally transpose in terms of how you write it down. To prove this result, I mean this is really not that big a deal, but A dot B, if you have a couple of vectors like that, the dot product, right, you do by taking these coordinates and pairwise multiplying and adding. This is how you dot vectors. And then, but think about how would you compute what's on the right-hand side here. How would you compute that? Well, you're going to take that A by transposing it and turning it into a row matrix, and then doing this matrix vector product. How are you going to compute this matrix vector product? Well, you're going to pairwise multiply and add. It's the exact same arithmetic, right? It's really just kind of notational sort of alternative, you might say, but it's computationally it's really identical formulas. So, like I say, this is a little twist that we haven't had any need for at the moment, which is why I hadn't brought it up. But anyway, here it is, and surprisingly convenient and multiple occasions, this being one of them. Notice then that's the first thing I've done here. I've replaced a dot product with a transposed matrix product per that formula. Okay, no big deal. And then just look how nicely everything falls into place. Recall, going way back, section 1.4, a transpose of a product is the product of the individual transposes. Don't forget to switch the order. Little oddity of how matrix transposes work. So, old fact. By associativity, I can group these together. I can do that inside multiplication first if you like. A transpose A. Don't forget A is orthogonal, and we just got through proving that for an orthogonal matrix, A transpose A is the identity. So that little product in the middle disappears in a puff of smoke, thus leaving us only with V transpose W, which because of that formula is V dot W as required. And that's all there is to it. And so it's just a direct calculation to show that this is the case. How are we doing? Let me hit the pause button again. Everybody happy with this? Okay. All right. So a little bit of algebra. Let me try to persuade you why we're interested in this. Then punchline: orthogonal matrices preserve dot products. What does this do for us? Well, here's the thing. Dot products in Rn are how you compute lots of stuff. Right? So if the action of a matrix is to preserve dot products, if all dot products are preserved by multiplying by this matrix, then furthermore, anything else that you can compute from dot products also preserved. Right? And let me just remind you, here are some things that you can compute with dot products, as we saw last time. Magnitudes, distances, lengths. Computed with dot products and square roots and stuff. Angles are computed entirely with dot products. So these orthogonal matrices don't just preserve some computational item. Orthogonal matrices, the action of multiplication by an orthogonal matrix, preserves almost all geometric quantities. Distances, angles, lengths, this kind of thing. These are what we call rigid motions, right? Rigid motions on Rn. So the multiplication by an orthogonal matrix, for example, might take Rn and it might maybe rotate it, something like that. It might flip, right? But there's not going to be any sort of, shoving, squishing. There's not going to be any stretching or shearing, nothing weird like that. all of Rn will stay rigidly arranged as it is and just possibly rotate or reflect. And that's all. All right, so it's geometrically very natural because of this result. Okay. All righty. A quick observation, and this is just for, in case you're curious, and we don't have time to spend, I would love to spend time talking about this. We just don't have the minutes. There is a remarkable, shocking result about the collection of all of these matrices. If you look at the collection of all orthogonal matrices and exclude the reflections, this is a disturbingly weird set in a way that I can make precise. And if anybody's curious, come talk to me after class. The argument is what I'd like to call a literal hand-waving argument. The argument involves doing stuff like this. And if you're curious, come talk to me. It'll take about 10 minutes. But it's not at all part of Math 216. You're not obligated. This will not come up on any exams. It's just in case you're curious. Okay, so here's a pretty reasonable question. We've seen some nice things that you can do with orthogonal, there I go, get it wrong again, that we can do with orthonormal bases. If you're doing business with an orthonormal basis, coordinates can be much easier to compute. That's awesome. It's really valuable, crazy useful. And also, orthonormal bases, right, have this other nice feature that they preserve distances. So really good things that happen if you have an orthonormal basis. So let's suppose the situation comes up where you have a basis that you come into by random means, whatever it might be, and you don't want to have to spend your life doing business with this random basis off the street. Right? You would like to have a special, but you'd like to take your non-orthonormal basis and turn it into an orthonormal basis so that you can do all your business in terms of the orthonormal basis, because doing business in terms of orthonormal bases is convenient, and don't we all appreciate convenience? So pretty reasonable thing to want to do. How do you orthonormalize a basis? And there's a great answer for this. It's called Gram-Schmidt Orthonormalization. Very first time I encountered Gram-Schmidt Orthonormalization, I looked at that word and I thought, oh my gosh. I mean, just on the basis of the number of syllables involved there, this must be a pretty deep idea. I was all prepared for something heavy, something extremely sophisticated and deep, and it's not. Gram-Schmidt orthonormalization is the most obvious, unsophisticated, seemingly, well, what else would you do, algorithm that you're going to see in this class. So please prepare for disappointment. All right? It is not a deep idea. What it is, and I will confess, is it's a tedious process. There is a component of tedium here. And so these problems, they're hard in the sense of, there's a bunch of stuff you got to crank through, and there's all sorts of potential to oops, right? So they're hard in that sense. But conceptually, this is not a hard idea. So here's the scenario we face. Let's suppose we start with a random basis off the street. Nothing nice about it. The vectors aren't orthogonal. They're not unit vectors. We have nothing good to say about this basis other than we have it, right? I would like to fix that basis. I would like to make it orthonormal so that I can capitalize on all these benefits. Here's the first idea. We're going to take the vectors one at a time. Yeah, sure, right? Seems like a easy way to deal with this. What's the first thing we're going to do with the first vector? Well, I have a vector that's not necessarily unit length. I would like to turn it into something that is unit length. So divide it by its own magnitude. You impressed? I hope not. It is perfectly easy. If you want to take a vector that's not normal and turn it into one that is, just divide it by its own magnitude. Okay, so now we have fixed one of the vectors. Now we have one fixed vector and one not fixed vector. What's the next thing we do? Well, this vector here, this vector is not good. It's got a problem. It's pointing in the wrong direction. So how about we fix it by identifying this vector, to what extent, what part of it is pointing in the direction it's not supposed to be, right? We're hoping to have something that's orthogonal. We're hoping for something that does not have a component in the V1 direction. So how about we identify to what extent does W2 point in the V1 direction, and then we throw that part away. Said differently, let's identify what we don't like and let's throw it in the trash can. Again, it's not an impressive strategy. This is a perfectly obvious. Well, of course that's what you would do. If something is something that you don't like, get rid of it. You do that. What's left over is a vector that is at least pointing in the correct direction. Right? We've gotten rid of that vector now. Now don't forget, of course, our first vector is already fixed. We have the benefit that these are orthogonal because I've threw away the part that isn't. Right? Y'all remember that old joke about how to sculpt let's say a dinosaur out of marble? You take a chunk of marble and you chip away everything that doesn't look like a dinosaur. Right? This is kind of the same thing. We want a vector that's orthogonal. Okay, throw away everything that's not orthogonal. Right? It's pretty direct. So we have something that is now orthogonal, at least. How do we deal with the fact that this is not normalized? Its magnitude is not necessarily 1. Again, please don't be impressed. We take that vector that's not normalized, we divide it by its own magnitude, and now it's normalized. And check it out, we now have an orthonormal basis, V1 and V2. Like I say, this is not deep water. This is, it's the simplest thing that we could possibly come up with to achieve the task that we're interested in. Okay. All right. Now, there's details. Let's, with this strategy in mind, let's talk through the details. The first one is easy. Taking a vector that is not normalized and finding instead the vector pointing in the same direction that is normalized, divide by the magnitude. Super easy. Old news. Y'all saw this back in Math 212 on like the third day of class or something. This goes way back. Okay. All right. Now, here's the chip away that everything that doesn't look like a dinosaur. So we have here, we started with this vector, W2. We're going to try to identify what is this vector here. What is it that I should subtract from the red vector W2 to get a vector that's at least pointing the right way? What do I subtract from red to get purple? I guess I could have chosen those colors more appropriately. Oh well. So no big deal to figure out. What is this blue vector? This thing that I subtract. We're interested in a vector about which we know two things, or I can figure out two things. For one thing, how long is that vector? Well, that vector, its length is, what is the component of W2 in the V1 direction? That's how long it is. Just look at the picture, right? Magnitude of that blue vector that I want to subtract. To what extent does W2 point in the V1 direction? What direction does this blue vector point? Well, it points in the V1 direction, of course. The whole goal with this blue vector is to identify how much W2 points in the V1 direction. So the direction vector is V1. So easy calculation there. The thing that I subtract to fix the direction that my vector is pointing, the thing that I subtract is that little formula right there. This is the kernel, this is the nugget, the big idea, the most important idea in Gram-Schmidt Orthonormalization is the thing that you're subtracting has a magnitude that's a component and a direction that's the obvious unit vector. So just make sure to remember those two factors. That's what you subtract, and then of course it's all downhill from there. You have this vector that's now direction fixed. That vector points in the correct direction. We want to find a unit vector that points in that same direction. You unitize per Math 212, and it is all over. And we now have an orthonormal basis in the form of V1 and V2. How are we doing? Is everybody on board? Just details. Okay. Last thing, I do have an example that I'm going to show you quickly, but harder question. Suppose you have three vectors. How do you deal with you have a random basis off the street in a three-dimensional inner product space? How do you orthonormalize? Good news. We're still going to fix the vectors one at a time. More good news. The way we fix the first vector, just like we did with two vectors. The way we fix the second vector, just like we did with two vectors. So the story for the first two vectors is exactly the same. Right? So we're going to start this question with presumably two vectors that are already orthonormalized, so they're unit vectors, or orthogonal to each other. We're going to consider this third vector that's pointing all sorts of wrong direction and has all sorts of wrong magnitude. How do I fix it? I fix it by recognizing that there's a couple things that I don't like about this vector, this W3 vector. On the one hand, I don't like the fact that it has a component in the V1 direction. It's not supposed to have a component in the V1 direction. We were hoping to make this orthogonal to V1. So to whatever extent it's in the same direction as V1, I don't like it. And to what extent, what is the vector component of W3 in the V1 direction? Same argument as on the previous page. There it is. And then the only twist is we have to recognize that, now there's another component. In addition to not wanting W3 to point in the V1 direction, I also don't want W3 to point in the V2 direction. There's a simple formula for how much W3 points in the V2 direction. So really, my complaint about this red vector in terms of its direction is, there shouldn't be any blue part and there shouldn't be any orange part. So let's just get rid of the blue part and the orange part. We subtract off that blue part, we subtract off that orange part, and what remains after you subtract is pointing in the right direction. So, that's the process. You could probably guess what would happen if you had a fourth vector. If you had a fourth vector, you would follow this process for the first three of those vectors, and then you would look at that fourth vector and say, hey, you know what? There's three things that I don't like about that fourth vector. That fourth vector, to some extent, is pointing in the V1 direction. To some extent, it's pointing in the V2 direction. To some extent, it's pointing in the V3 direction. Then none of that should be there. Identify those components, subtract them off, and then you'll have a vector pointing the right way. Same general strategy. Okay. There's a detailed example here. This is just numbers. I want to point to one very quick thing about this calculation. Real quick, that first vector, normalize. Math 212. No big, right? Secondly, this second vector. Let me get my colors straight. That second vector there. I'm going to subtract off of that second vector the V1 part of it. There's that formula for the V1 part, and this is just details here. Don't forget that V1 vector we just computed. The V1 vector we just computed, so there it is. Dot, multiply, arithmetic, fractions, right? A bunch of details, but it's just arithmetic. Okay, here's the one thing I wanted to talk about. Fixing the third vector. Notice you got to subtract two parts, right? Just like we discussed. The normalization at the end. It's just arithmetic, but there's a nice little shortcut that I can show you. Here's the unnormalized. vector. This is the thing that I need to divide by its own magnitude. And you can divide it by its own magnitude like this. Identify what its magnitude is and then divide by it. That's the blunt, brute force, obvious way to do it. But here's the really cool idea. Notice that if you have a vector, any vector, you can multiply that vector by any positive scalar, I don't care. Any positive scalar. And take that and normalize, and of course you get the same result. Right, so the big idea, if you normalize that purple vector, you get the green vector, or if you normalize the orange vector, you get the same green vector. So don't just take the vector you're looking at and normalize this, fooey on that, multiply by positive constants in order to make your life simpler. So for example, I'd like to multiply by 5. So let's consider instead 0, -8, 4. It'd be a lot easier to normalize that vector. It's going to give us the same answer. Oh, I got an idea. Let's divide through by 4. I could instead normalize that vector. I'm just multiplying by positive constants. Conveniently, if you get rid of a bunch of common factors and fractions, the common denominators and stuff like that, the normalization becomes much easier. So consider using that little trick. Everything else is arithmetic, and that's it. Okay, see y'all later. Have a good day.